So example 2, again we're asked to solve the system using the elimination method. So again, to solve the system we need to keep in mind what we're being asked to do. So we want to find all, again, ordered pairs, since our system has x and y's for our variables, that make both equations true. So we're asked what happens on this one if we simply add the left sides of the equation together and the right sides of the equation together. So again, if we take our 2x minus 3y and add to that the quantity 4x plus 5y, and add 1 and 13 on the right sides of the equation. And so again, 2x plus 4x, we're going to get 6x. And a negative 3y and a positive 5y, we're going to get plus 2y. And 1 plus 13, we get 14. Okay. So then we're asked, did we get an equation that's easier to solve? And the answer to that is no, because this still has two variables. Okay, so in the elimination method, after you've done your first step, we should get an equation with a variable eliminated. So we started with a system with x's and y's, and if we do our steps correctly, we should end up with an equation with just an x or just a y. But we can see here that this one still has both variables in it. So we first need to use a property of equality on each equation so that we can make the coefficients of one of the variables opposites, like they were in the last example. That way, when we add our equations together, one of the variables will be eliminated because its coefficient will be 0. We want to make sure that when we add the sides of the equations together, that a variable is eliminated, resulting in an equation that's easier to solve. Okay, so if we take a look at the system that we have, and let's say, and again, it doesn't matter which variable we choose, so I'm just going to say here we're going to eliminate x. And so to eliminate x, we need the coefficients on x to be opposites. So here we have a coefficient of 4, and up here we have a coefficient of 2. And now it would be much nicer if this coefficient were negative 4, because a negative 4 and positive 4 would be opposites. And to change a 2, to get a 2 into a negative 4, we would need to multiply by negative 2. Okay, but we need to use a property of equality to make sure this equation is still equivalent to the one that we started with. So we're going to take that first equation and we're going to multiply each side by negative 2. Okay, so that's going to give us negative 4x plus 6y equals negative 2. So there's our first equation that we had up here. And now if I pair that with the second equation, 4x, which again is implied to be positive if there's not a sign, plus 5y equals 13. So now, since we used a property of equality to make this coefficient on x be the opposite of the coefficient on x in the other equation, now when we add these, negative 4x and a positive 4x, we're going to get 0x. 6y's plus 5y's is 11y's. And a negative 2 and a positive 13 would give us an 11. So again, 0 times x is just 0 plus 11y, so we'll get 11y equals 11. And if we divide both sides by 11, we get y equals 1. So now again, if we go back up and see what we were asked to do, solve the system, means we need to find an ordered pair that makes both equations true. Okay, currently we do not have an ordered pair. We only have the y equals. Okay, so we're going to go back up now, switch it over here. And we saw in the last example that it did not matter which equation we pick. So I'm just going to take the first one. 2x minus 3y equals 1. Okay, and we're going to replace y with 1. So we're going to get 2x minus 3 times 1 equals 1. So 2x minus 3 equals 1. And to solve for x, we would first add 3 to both sides. 2x equals 4, and then we divide by 2 and get x equals 2. Okay, so to solve the system, we were after an ordered pair. So we're going to see if this ordered pair we got, and again, ordered pair x comma y, so x was 2 and y was 1. So we're going to verify that this really is the solution to our system. So we're going to take our first equation, 2x minus 3y equals 1. Substitute 2 for x and 1 for y. We're going to get 4 minus 3 is 1. 1 equals 1 is true. Okay, so our point makes the first equation true. Okay, but to be a solution to the system, it does have to work in all of the equations in the system. So we're going to try the second equation. So again, we're going to substitute 2 for x and 1 for y. And we get 8 plus 5 equals 13. So 13 does equal 13. So again, we have an ordered pair that made the second equation true, and the first. So the solution to the system is this ordered pair. Okay, this ordered pair makes both equations in the system true. So again, if we were graphing these equations, what is happening at the graph at this point? Okay, so again, this would be our intersection point. So the same method, so in the first section we looked at using the graphing method, and all the methods are going to arrive at the same solution. It's just sometimes one method might be preferred to another. Okay, so in this case, these aren't really nice coefficients to try to find some xy's to maybe graph these two equations. But using the elimination method, we found, again, the solution to the system is the pair 2, 1. So again, if we were to think about graphing these, this would be where that intersection point is as well on those graphs.